All right, so next on your schedule is homework number 10, and that assignment is due on Wednesday of next week, and it's available right now on Blackboard. What I'm asking you to do in homework number 10 is identify a watershed that's interesting to you, and it should be a separate watershed from the one that you analyzed in your previous homework assignment. Identify a watershed, and my suggestion is that you find one that is probably no smaller than 50 acres, because what I'm going to ask you to do is to calculate a composite curve number, among other things. And if you have a really small watershed, then your composite curve number won't include much variation of different land use soil type polygons. I'll show you today what I mean by that, but 50 acres is maybe the smallest that you ought to select for the watershed that you do in homework 10. So I'm asking you to develop like a user guide for yourself, because I can speak from experience that when you set WMS aside for a couple of years and now suddenly there's a project where you need to use it, you're going to forget basically everything you once knew. I've forgotten and retaught myself how to use WMS 5 or 6 times over the course of my career. So what I'm asking you to do in homework 10 is make a guide for yourself how to do the rational method, how to do NSS, and TR55. And it's more than just screenshots, but you need to include like explanations and like a written overview of the process. And so it's not only demonstrating to me that you know how to do that, but it's also kind of a tool that you'll be developing for yourself with an example watershed. So look up the description. That's available now on Blackboard, and it's due Wednesday of next week. What we're going to be doing today is working with a watershed in Morgantown, West Virginia, to go through the process that's used to calculate a composite curve number for a watershed. And we had to kind of rush through TR55, so we'll be calculating those curve numbers in order to generate a TR55 model and get a little more experience using that. Before we begin, are there any questions on the announcements? All right. Well, the watershed that we are going to work on is the West Run, which discharges into the Monongahela River in Morgantown, and there is a high-resolution data source for soil type information you've used before, Surgo. You used that from one of your previous homework assignments, and so you're familiar with what those soil polygons look like. And we're going to also utilize the National Land Cover database, and then there's a curve number table available on Blackboard. So you should get that now. It's available on Blackboard. It's near the bottom of the list. I think it just says curve number table. It's a text file, and so just download that so you have it at the ready. Maybe open another tab and go over to the curve number table. If we open it up, just to show you what it looks like. That curve number table is just a text file, and what's in it is this. So you're going to need that a little bit later today to do some of the curve number calculations. I think I've showed this to you before. What it includes is different land uses found in the state of West Virginia, combined with their type A, type B, type C, and type D curve numbers for the hydrologic soil group. So we're going to need that. WMS is going to need that to calculate curve numbers a little bit later. All right, so assuming you've got that curve number table now, go ahead and start the WMS program. And I was really pleased, by the way, with how everyone was able to delineate the watershed. I was anxious that maybe some people wouldn't be able to find the outfall of the watershed, but everybody got it, so I was happy about that. Alright, so let's start up the hydrologic modeling wizard, and create a new project file name. So save your work so you have this demo available in some new folder. So let me go up, and I'm going to call this, today's Monday the 10th class. Alright, so click the Save button, and then we see that the file name is created, and we'll click Next. Alright, so the project boundary, make sure that you have the projection set, and define the project boundary. Let's look for Morgantown, West Virginia. Jump to the search location. There it is, Morgantown, West Virginia. Alright. Sometimes when I mention Morgantown in live classes, people kind of roll their eyes and groan a little bit, like it's a place that they don't like for some reason. I think Morgantown's kind of cool. It's hilly. It makes me glad that Huntington area isn't that hilly. Okay, so the watershed that we're interested in, you can already kind of see it here on the screen. There is a creek that discharges, that's more of a creek, it's more of a river than a creek, but West Run discharges into the Monongahela River. And so we want to delineate what is the area that contributes to the flow here at West Run. So we're going to, when we get the chance, we're going to drop an outlet, a little bit away from the combination. If you drop the outlet too close to the union of West Run and the Monongahela River, things get screwy. If you put your watershed outlet in the river, it's so flat, then it would start reaching really far upstream and downstream to include in your watershed. So you have to, pay careful attention to getting a couple of elevation blocks away from where those get together. And so we don't have the whole watershed here. We're zoomed in too far, so let's zoom out a bit further. And this may be an iterative process. I was looking at it earlier today, and I think if we're zoomed out about this far, we'll get it all. Alright, so I don't want to have the focus of today's class being us repetitively zooming out and panning, but I'll point out that there is a section up here at the top that it kind of extends out to the north much further than you'd expect. And so what I'm hoping we've done is got all of that boundary. So let's see, if I go that far, I think that's too far. Let's give it a shot here. And if we don't get the whole watershed in this particular case, I'm not going to sweat it, because it's really more about how to use the WMS tools to calculate curve number. Alright. So with this area defined, click OK, and what it'll do is it'll feed those coordinates in to your boundary, and you may have to minimize and then re-maximize again to get the wizard on the screen. Sometimes for whatever reason that wizard will get forced into the background. So click Next, and make sure that you have enabled the Use Web Services, and we're really going to use them today. We're going to download several data files that are cached on the Aquaveo server. It'll be so much easier for us in particular to get the soil type data compared to what we normally have to do interacting directly with USDA. We're going to be really glad to be using WMS today. So click Next, and now what we're going to download is three different things. We want to get the elevation data, so make sure that you have that selected. We're going to get the National Land Cover Database 2011. Now, this is one thing that kind of bums me out, is I think that there's more recent NLCD data than 2011 that WMS hasn't yet got loaded up. So hopefully they'll do that soon, because the forward march of so-called civilization with lots of more land development and more urban area taking out what was previously wild, then the land cover can change over time. So 2011 is the best that we've got, and be sure that you also have the Surgo soil type enabled. Now it's not StatsGo that we want. StatsGo is a lower resolution soil type database. We want the Surgo. So with those three selected, click download data from web, and when you do, it's going to ask for the resolution of the elevation data. And normally I tell you just click OK, and it would be fine if we did, but just to show that we can select more resolution than the initial suggestion, let's go from 30 meter pixel resolution to 14.7 meter pixel resolution. So what that'll do is that will make each of our elevation cells a little bit smaller. It'll give us a little bit of a finer razor to trace the watershed boundaries, and it'll give us a little bit better chance of avoiding the Monongahela River when we place our watershed outlet for the watershed that we're interested in. So it'll take a little bit longer to download, so don't be worried if there seems to be a delay. So click OK on that, and then it's also going to prompt us what resolution scale we want. This time it's asking for the NLCD. So it's asking, do you want to maybe downsample the raster that it will bring into the background for our land use data? And we don't. Just select OK for that. It won't ask a third time because the Surgo soil data that it's getting right now, you can see the message that's on screen for that. Surgo isn't a raster, meaning it's not a picture. It's not a series of pixels. Surgo data is vectors. And so those are shape files that are kind of infinitely precise. You'll notice that something's been downloaded into the background there. Let's close the wizard and explore what has been added. Also, I'll point out over on the left side in the Project Explorer, it's added some additional files that we don't normally see. So for instance, you'll notice that it's now added a land use coverage, and we have these soil type files, and in addition to the typical elevation heat map that it gives us, there's also the National Land Cover TIFF file. So to explore, let's start with these shape files, these soil shape files. Turn off the bottom one, the 611, and you'll notice that 611 overlaps with our elevation data. And so one of the strange things is that I guess WMS is worried it may not get all of the soil data that you need. So when you're on a border of two different counties, it'll download both counties. And so we're close enough to two counties. It went ahead and got the data that we need and this data that we don't. And so just to simplify things, oh, by the way, let's save our work right now because we're going to be doing some heavy lifting today. So anytime you do heavy lifting, there's a chance the program could crash. And so let's save. And let's remove, now that we've saved, let's remove this soil data that we don't need. And so the way to do that is right click on the name of it. So right click and delete. Okay, so it's gone. And for that matter, for now let's just turn off this soil data. We're not deleting it, we're just turning it off. And then zooming in on our project area. Let me pan down a little bit. Okay, so let's turn off this elevation heat map and turn off the National Land Cover database. So this heat map we've seen plenty of times before, and you know that I'm not particularly impressed with it, so I'm going to delete that as well. Let's just remove it. Don't need it. Alright, so save the file again. And what we usually do at this point, once we have our elevation data, is run Topaz. So let's do that. Turn on the wizard again, and let's skip down to compute flow directions and accumulation. And my suggestion is set the accumulation threshold to 50 acres. and then compute Topaz, and it will go through it relatively quickly. And click close. And so if we close this, we see this is the outlet that we're going to be setting. And just to make sure that's the right thing, let's turn on the map, the world street map data, click OK, and then as it loads we can zoom in a little bit. And let me turn off the elevation contours just to make it a little bit easier to read. Yeah, that looks familiar. That is the west run that we are going to, let me turn on the elevation data again. So those blue lines are the flow accumulation cells where WMS is predicting, based on the elevation data, is predicting where the creek would form. And that is where the creek forms. Now let's take a moment to take a look at some of the other data that's been downloaded besides the elevation data, which we've seen before. So if you turn this soil shapefiles back on, so you click that, you'll notice that suddenly we have all of these polygons that each one of them is going to have a different hydrologic soil group. And so we could click on those right now with this identify tool, and it might give us a little bit of an idea of what's in each one of these individual polygons. And you've seen these abbreviations before. Here it's saying MGC. Those abbreviations are related to the soil properties that are assumed to be in that location by virtue of like the elevation data and extrapolation from what is known about the typical soils in that location. So it doesn't yet have a hydrologic soil group associated with it, and it will later, but you can see that you can click around at different spots and find out what soil type is in a certain location. Alright, so that's one of the things that we've downloaded new today, is the soil data polygons. Let's turn that off. And then turn on NLCD. And we have to turn off the street map to see it because the street map is being drawn on top of NLCD. So turn off the street map. Alright, so there's this colored map that will make a little more sense if we let's zoom out like here. Alright, so what do you suppose red means on this colored map? Let me turn off the elevation contours just to make it a little bit easier to see. So what do you think blue is? Well, blue appropriately represents water. You know, that's where we already kind of knew that the Monongahela River was. And so if I turn that street map on, it'll draw it on top, and it's going to verify, yep, that's where the river is. And wait for a moment for it to stream that map to us. So looking at this part of our street map, that's pretty urban, whereas out here is relatively rural. So if we turn off the street map and again gaze upon this National Land Cover Database file, the red areas correspond to a land use that is urban. The green areas correspond to a land use that is rural. And so each one of those colors is going to be coded to the table. This table knows how to interpret the colors to find out whether it is pastured / hay, cultivated crops, mixed forest, evergreen forest, deciduous forest. And so each one of those colors has a number associated with it. And so WMS reads, for example, maybe 21. When WMS sees the number 21, it gives it a color, just because that's an easy way for us to visually identify that, developed open space. But what in the background the number 21 would mean is it would mean use this row for when you are overlaying the land use and the soil types together. So here, if I turn on the soil type polygons, you can now see we've got that soil type overlaid on top of these land use associations. And so what WMS is going to be able to do is it's going to know how many of these soil areas are on top of, like how many Class A soils are on top of forested area, how many Class A soils are on top of urban area, and it's going to do like a weighted average of the curve number based on the entirety of the data that's available here. So that's a little bit of background. Let's turn that off because we haven't even yet defined our watershed. We've done Topaz, but we haven't dropped the outlet and had it delineate the watershed, so we need to do that. So let's start the wizard back up, choose outlet location, and I'm going to zoom in a little bit more before I drop that outlet point. So create outlet point, and I'm going to put it right here. All right. Not in the river itself. Alright, so next, and then click delineate watershed, and it'll have to think a little bit longer than it normally does because we chose the higher resolution elevation data. We wanted the 15-meter elevation data rather than the 30-meter elevation data. So you'll notice that it's going through these calculations kind of slowly and ponderously, but it'll be done before you know it. As it's computing the maximum flow depth, what it's doing is it looks like I don't have the whole watershed. What it's going through, I went too far to make sure that that north part was in, and I lost some of the southern part. But we won't do it over again because it's really about calculating the curve number today. But you know what to do in a situation like this. You'd pan the project area a little bit to the north so that you'd get some of the stuff to the south restored. Alright, so this is our watershed area, and if we pull up the wizard again, we're going to go into some territory that we haven't been before. Delineate watershed, next, select the model. So in the drop-down box, choose TR55 and click Initialize Model Data. And there's other ways to do this. You can go directly into the hydrologic modeling module and select TR55 from the drop-down box. So you have done that before, but this is just a way to tell it to switch into the hydrologic modeling module and that we're going to be using TR55. So it's in a way, it's a shortcut. Okay, click Next. Now this is where, remember when I was clicking with the info tool on the individual polygons, it was telling me the abbreviation for the soil, but it didn't yet have a hydrologic soil group assigned to it. So this shortcut, that data file does exist. If we look at, like what have we downloaded so far, I think that this is the subfolder that I've been working in. The soil type data that I downloaded was this Surgo, and if you click in that, the Surgo has a lot of different database files. So there's lots of information here, and one of them is the NRCS data, the hydrologic soil group. So what happens when you click on this Join NRCS, when you click there, it is going to combine each polygon in our system with its corresponding hydrologic soil group. And so make sure that Join Hydrologic Soil Group is enabled. Soil texture we don't need for the curve number calculations, but it can be used for some different applications within WMS, and so there's no harm in joining it as well. Occasionally there will be some areas that you don't have the hydrologic soil group assigned, and so you can force WMS to make an assumption if it finds any blank, any of those polygons that don't have a hydrologic soil group. And so I'm going to click fill blank values, and I'm going to fill it with soil group D. So what that means is that if it finds any cell that doesn't have a hydrologic soil group, I want it to write in that empty location soil group D. Alright, so click OK, and then click on create coverage. Now right now, how many coverages do we have? Look over on the left side in the Project Explorer. We just have right now only a drainage coverage, and what's inside that drainage coverage is the boundary of our watershed that was created when we delineated the watershed using the delineate watershed tool. So it was based on the elevation data. So we only have one coverage right now, but if you click create coverage, now you'll notice that there's also a soil type coverage. So there's over on the left side the drainage and the soil type. So in the soil type coverage, what it's done is it copied over the polygons from this GIS data file into a coverage which can be used for the curve number calculations. So it's kind of copied and pasted the important stuff that we need, and it's not going to look at all the other database files that are there. Alright, so click next in this tool. We're going to be matching together we're going to paste into the soil type coverage the shape file from that county shape file. So click next, and then the important thing here is hydrologic soil group is going to be mapped out of a data field that it's found in a text file for the SCS soil type. So it's got all these different soil types, B, C, D. So click next and finish. And so now it's doing that joining. So now those different polygons have colors associated with their hydrologic soil group. And we've got the coverage created, so click next. And now what we're going to do is we're going to compute GIS attributes. So this top button here, click that, and we're going to create the curve number. So we want to calculate the curve number using coverages. So soil type is going to be determined by this soil type coverage that we've just created. So it knows the default there. The land use is going to be a grid, and this land use grid is the National Land Cover Database. And so the important numbers that I was telling you about earlier from that map have been copied into the land use grid. So it knows to look at National Land Cover Database for the grid. It's going to be using the USDA soil data that we've downloaded and pasted into the soil type coverage. And so we have to import that text file that I shared with you on Blackboard. So click import, and it's just giving you this warning message. We're going to overwrite what's there already, and that's fine because what's there right now is just a bunch of zeros. So click OK and browse to the location of that text file. Let's see, I think I put it in one of these, not that one. There it is. Alright, so when you click open, now if you scroll down through this box, you'll notice that it has a soil group A curve number for all of these different land uses. We've got B, C, D. So this is the table that's going to assign everything. And when you click OK, it'll prompt you that it open up the data file that it's creating. It's just a little report, and it's a text file, and you can use Notepad to open the report. And it's telling you where it's been temporarily saved. So click OK, and then in this report, it's telling us for the watershed the composite curve number. So this watershed down at the bottom, you can see that it has a composite curve number of 68.7, and all of the curve number, area, and then it's computing a weighted average by multiplying the curve number for a certain overlapping land use and soil type by the respective area for that land use and soil type, and calculating the weighted average down at the bottom. So our weighted curve number is 68.7, and if you like, you can save this for later somewhere, that curve number report. And we computed the GIS attributes, and now we're going to use the curve number that it calculated, the 68.7. If you click using basin data, then let's calculate the lag time using the SCS method, and it automatically fills in the applicable watershed slope, the watershed length, and there's even the curve number that we just barely calculated. So based on those variables that are determined, then it's going to calculate the time of concentration for us, and click next, and we have to tell it how much rainfall is going to go into our TR55 model. And I think if we, let's see, compute, let's define the precipitation. And so the precipitation amount goes in the TR55 window here. So let's say that we had gone to get the precipitation data, and what was it from the exam? Anybody remember what was the 5-year precipitation amount on that exam question? I don't remember the depth. Oh, I just noticed a question from Jeffrey. The higher the number, the more developed the area is. Yes, that's right. A high curve number means that it's more developed. Let's use a rainfall depth of 3.5 inches just to get a feel for that. And of course we know that the rainfall distribution is type 2. In our watershed there's no ponds and swamps, so we'll leave that set to 0%. And then what it calculates the peak discharge here at the bottom. So what we would see is, for this watershed, where we know the time of concentration because it's been calculated, we know the drainage area because WMS delineated that for us, we have the repeatable, defensible curve number that's based on like data that is government generated, and it's not just us taking a stab in the dark. That 68.7 is about as quantitatively based as anything in hydrology. Now we have our peak runoff would be 1000 CFS, and if you click on compute hydrograph, click that button, and then let's click OK here and close the wizard for now. That's kind of looks like a big spaghetti mess right now. It's kind of hard to see, and so we can turn off the soil type polygons and click back over to the drainage coverage. And if you go into the hydrologic modeling module, you can see that the hydrograph is on the screen there, and so double clicking on the hydrograph icon brings it up, and then if we wanted to, we could go through that process of exporting the hydrograph. I mean, you could just take a screenshot of this, or if we wanted to plot the data, export/print, then we would take the text to a file and put it where we want it to be saved. Maybe I'm going to save it in Monday the 10th, and I'll call it hydrograph export txt, because I'm going to open it with Excel, export, and I want the table as points and subsets, and click export, and then it creates that file. Alright, so it's 9:49. We're out of time for today. I know that's a lot, going through the process of calculating the curve numbers from the land use and the soil type, and if we want to look at those soil type polygons, there they are. We can turn them on, and if we want to take a look at the land cover database, then we can turn that on and turn off the elevation map and see the overlap of our land use and soil type. So that's it for today. Let's just take one last look at these announcements. The homework assignment number 10 is asking you to go through rational method, NSS, and TR55 just to get the practice with those approaches, and also calculate a composite weighted curve number for a watershed that you're interested in. So you can get an early start on that. And if you have any questions about this or the exam, feel free to let me know. But otherwise, I will see you on Monday. Hope you have a good weekend. Bye-bye.